Yo, what's up everybody? This is Ethan and welcome to my channel Brain Flux. On this Brain Flux, we're going to be talking about reversible reactions and equilibrium right after this.
Again, that's why I got more verses than Genesis. I guess he gave me this gift to remember him. You gotta find your diligence and execute it with energy. Cause if you influencing anything else, you only a hindrance.
Okay, now let's get into it. What is a reversible reaction? Well, a reversible reaction is a reaction where the products can reform the original reactant, or in other words, it can proceed in both directions, the forward direction and the backwards direction. So if something can be made into a product, and then that product can be converted or may be remade to the original reactant, we can say that that reaction is reversible. Okay, now let's look at an example. If we would have hydrated copper 2 sulfate, which is blue in color, and then heat it up, we'd get this white powder which is called anhydrous copper 2 sulfate. Now if we'd get that anhydrous copper 2 sulfate again and then put water in it, it's going to turn blue, which is the hydrated copper 2 sulfate. So this shows that this reaction is reversible since it can proceed in both forward, which is when hydrated copper 2 sulfate becomes anhydrous copper 2 sulfate, and the reverse where anhydrous copper 2 sulfate becomes hydrated copper 2 sulfate. Now reversible reactions can be shown using the reversible reaction symbol, which is basically just two half arrows pointing in opposite directions, which just shows that the reaction can proceed in both forward direction and backwards direction. So now let's talk about equilibrium reactions. So these are ones where the reactants produce products, but those products are reforming to give us the initial reactants. So we actually see this in hydrogen and iodide actually reacting together. It gives us a mixture of hydrogen and iodine with hydrogen iodide, something sort of like the reaction didn't reach completion. But as for this one, what is actually causing this is that at the exact same time as hydrogen and iodine are actually forming to give us hydrogen iodide, that hydrogen iodide is actually disintegrating or decomposing to give us our hydrogen and our iodine. So this is an example of a reversible reaction, but in this case, instead of happening at two different intervals, it happens at the exact same time, and we classify this type of reversible reactions as equilibrium reactions. Now, during the manufacturing of fizzy drinks, carbon dioxide is dissolved into the drink at extremely high pressure. Now, when you take the lid off the bottle, you're going to see effluence or carbon dioxide bubbles start arising. Now, when you put the lid back on, the bubbles immediately stop. Now, this is a very good example of equilibrium. Now, the forward reaction is predominant during the manufacturing of the fizzy drink, while the backward reaction is predominant when you take the lid off the bottle. Okay, now let's look at some characteristics of equilibrium reactions. Now, the first one is that these reactions are dynamic. So, what we mean by dynamic is that the particles of the reactants and the products are continuously reacting. So, it's going to seem as if, nothing is happening, but in the actual case, the particles are like interacting with each other, where while the products are reforming the original reactants, the reactants are also producing the products. The second thing is that they occur at the exact same rate. So what we mean by this is that the rate of the forward reaction is equal to the rate of the backwards reaction. So in this case, where we have these four molecules on the left and all these 8 atoms on the right, as one molecule decomposes to form 2 atoms will also form one molecule in a given second. So that's what we mean by the rate. The time at which the forward reaction is happening and the time rate at which the backward reaction is happening is equal. Now, the third thing is that the concentration of the reactants and the products remain constant at equilibrium. Now, due to the fact that the rate of forward reaction is equal to the rate of backward reaction, the number of particles of each substance remains the same. So that's the reason why their concentrations are constant. And another thing about equilibrium reactions is that they're supposed to occur in a closed system. So now if we look at the example of calcium carbonate decomposing to give us calcium oxide and carbon dioxide, we see is that If the system is left open, it won't be an equilibrium reaction, but when the system is left closed, the reaction is equilibrium.
Every time I step in a